we'll move on to our second speaker, who is Marco Delbo. Marco, are you online?
Yes, I am. Hello.
Great, great. And so Marco is going to be presenting on observing the planetesimal size distribution amongst main belt asteroids today.
Okay, I'm trying to share the screen, hoping that it's going to work. Right, I hope you can see it.
We can, thank you so much.
Okay, thank you. So first of all, thank you. This is a project that we have been working on for some years, and it's funded by the National Agency of Research in France. And some of us are also members of external international co-eyes of the survey class project, is led by Dan Britt of the UCF. So I'm going to talk about one of the most fundamental problems, I would say, of planetary formation and the lives of asteroids. And that goes back to the questions: what are the typical sizes of the planetesimals, what their composition, and if they can still find them in our solar system. And the planetesimals are, let's say, the theoretical objects, the first stage of formation of planets. And there's a big debate in the community about their sizes in particular. And while this problem is typically addressed, let's say, theoretically, our idea was to try to locate them as many as possible in the main belt. To see how this works, I would like to introduce the asteroid formation paradigm, which is basically telling us that the asteroid in the main belt that we see today, some of them formed directly from accretion of dust in the protoplanetary nebula. And they are accreted in different regions and in different sizes, probably, with different compositions, and which I painted here in this cartoon with different types of asteroids and colors. You can see a high albedo asteroid and a low albedo asteroid. So those that accreted directly from the dust are planetesimals, right? So, but throughout their lives, asteroids can experience impacts, and some of them are catastrophic impacts. And so the first asteroid on the top might break and create a family of fragments. These family of fragments are themselves new asteroids created from the disruption of this original planetesimal that does not any longer exist in the main belt, but just its let's say its daughter asteroid. And however, some asteroids might not experience this catastrophic, some planetesimal might never experience this catastrophic breakup, and so they're still there in today's main belt, preserved as they were originally formed in the protoplanetary disk. Let me just draw your attention that there are families of fragments that have different albedos, different composition, which are painted here, one white and one black. And I also want to address the problem, just to show the problem that the collisional families of asteroids, that their members diffuse with time in orbital elements. And so the families start, as they age, they start to overlap among themselves and also over the original asteroid. So the picture is very confused, as you can see in this third diagram. So it would be amazing if we could find the survivors, because if you can locate the original planetesimals, the asteroids that are planetesimals, getting rid of all the asteroids that are family members that were created after by the collision, we could actually get an idea of the original size distribution of these planetesimals, which is a tremendous, important constraint for planetary formation model. You can read these papers by Morby, Sean Raymond, and Anders Johansen, and so on. They're many with this topic. So let's look at the belt. Here we see a distribution of the asteroid in the belt in proper semi-major axis as function of the inclination, proper inclination. The asteroids, each point is an asteroid, and they are colored with a palette according to their albedos. These are essentially data from WISE, Nakari, and IRAS. You can see by eye that there are clusters, and these clusters, they're also clustered in albedo. These are the asteroid families. And there are techniques to identify the families. So one could think that we could try to identify all the families. Here we see only the inner part of the main belt. So between the Nu-6 secular resonance and the 3-to-1 mean motion resonance with Jupiter. And we see different orbital plots. Okay, so we can use the hierarchical clustering method to basically grab these clusters that I highlight like this. And then let's try to play this game. So let's remove them. And ideally, we would love to see this. So a bunch of planetesimals that are there and they were never catastrophically broken up. And so once we remove the collisional products, we should see the original asteroid. But unfortunately, it's not what we see. We see something else that is more like this. So we see a crazy background that has a lot of structures. These are halos of families that have first identified by Alex Parker and co-author in 2009. But what are them? Are these very small planetesimals? Or there are, since they have structure in orbital element space, they could still be undetected, very ancient families. So we try to identify collisional members with a different technique. We use the V-shape of the Yarkovsky effect. If we actually take the members of a collisional family and we plot their semi-major axis, we plot their inverse diameter, so 1 over the diameter, as function of the semi-major axis from the center of the family, for instance, we see this kind of V shape. They look like a V, which with the vertex of the V pointing to the center of the family. Here we see in the y-axis, big asteroids are to the bottom near the 0 because it's 1 over d, and to the top, it's around 0.9, 1 over d is almost the size of a kilometer. 0.5 is 2 kilometers, 0.1 is 10 kilometers, and so on. The main important thing is that the Yarkovsky is this non-gravitational force that pushes asteroids in two directions, depending on their rotation state, and also depending on their sizes. And so large asteroids, they don't move, whereas small asteroids, they move much more. And so if we let time goes by, we see that the V shape expands like this. We can also measure the age of the family by simply fitting the border to the V shape. So our idea is to basically locate asteroid V shapes in the main belt. And you can see here another cartoon showing a bright V shape, high albedo V shape against a dark V shape. And the asteroids that are not inside the V shape, they could be the original planetesimals because all the members of V's are collisional products, whereas those that cannot be put in V's are the planetesimals. And so we can, thank you. We can reconstruct this game and go back to the original asteroid, of course. So I think I will skip a little bit how we do this identification of V-shape. You can actually find the paper by Bryce Bolin and by myself in 2016 and 2017, and I come directly to the point. So we have identified a series of V-shape that were not seen before, and here's one. So you can see here, I don't know if you can see, I can draw the lines just to guide your eyes. There are 3 V shapes here. One, the blue and the red, they were known before. They were identified by Walsh et al. And Kevin Walsh, myself et al. In 2013. But in 2017, we identified this very wide V shape that basically spans over the entire inner portion of the main belt. This is only low albedo asteroids. So we think that these are all collisional families. And the wider one could be as old as the solar system. But the most interesting thing, well, one of the other interesting thing are these asteroids that just made them square that are outside the V shape, and there's no way to put them inside V shapes. These are planetesimals. So we went on and we identified more V shapes. Here's another paper that we published in 2019, where we identified 2 more V shapes in the inner main belt with intermediate albedo, and they are also bounded by other asteroids that cannot be put in V shapes, and these are for us the planetesimals. So we can start to reconstruct the planetesimal size frequency distribution of the original planetesimals in the inner main belt, and it looks very, very shallow. It's very, very shallow, not like -2, but is shallower than -1. If we, I'm almost to the end, if we fit a function to this distribution, we see that the PDF, the probability distribution function, correspond to a Gaussian centered around 80 kilometers with a wide distribution around 50 kilometers. So basically, these are the conclusion. I just leave it there, and I conclude saying that if this work shows that the planetesimals were essentially born big, with a diameter around 80 kilometers, and the smaller asteroids essentially are all collisional products. And I take questions if there are.
Great, thank you so much, Marco. Are there any questions from the audience? Don't see any raised hands. Quickly, Marco, could you describe any follow-up observations that would be helpful in pushing this work forward?
Yes, we are doing that, and it's a very interesting question. So there are a number of things. One thing is interesting. Our list of planetesimals is public in the paper, and we can give to anybody who's interested. And it's interesting because they can basically, for us, these are the objects that form accreted directly in the protoplanetary disk. So it's interesting to see what their spectroscopic class is, what is their composition, and so on. Another interesting thing to do is to, let's say, constrain the composition of the families. So I know that some of the guys from your university are following up our families to prove or disprove their compositional homogeneity. And I think these are very beautiful things to do.
Great, thanks so much, Marco.